Hello and welcome to my channel. I am the Mad Computer Scientist. If you are new to this channel, please like, comment, and subscribe. If you find this video useful, please share it out with your friends. And today we're going to talk about something known as Big O notation. Now, if you're snickering a little bit about this, it's okay. I still do it from time to time, but it's probably not what you're thinking about. Big O notation simply stands for big order, or omega. And we're going to go over what it is in the next couple of slides. We'll even have some math fun along the way for those who are interested in that sort of thing. If you have finished snickering from the previous slide, you're probably wondering what Big O notation means, and that is a good question. It refers to how quickly an algorithm runs in the worst-case scenario. Computer scientists use it to determine if one algorithm is more efficient than another algorithm. If one algorithm is big O of another algorithm, we want to use the algorithm that isn't big O, and we refer to that as little o. A good example of an algorithm that has a bad big O runtime complexity, but a good average runtime complexity is merge sort. In the worst case scenario, merge sort is n squared, and that means it's big O of n squared, although the average runtime complexity is little o of n log n. And by the way, in computer science, usually if we're referring to logarithms, we do use base 2. If we're using a different base, we'll tell you. Keep in mind that capital O refers to big O, and the lowercase o refers to little o. This can also be referred to as big order and little order, or by using the Greek letters capital omega and lowercase omega. There are broad runtime complexity categories, and generally if you find runtime and even space complexity, which is also referred to this way, you'll see them expressed this way. All of these can be graphed in a certain way. For example, if we have O1, that means the algorithm runs in constant time, and its graph will be represented as a straight line. O log base 2 of n is logarithmic time, and this is the runtime complexity we want to use if we're dealing with large data sets. This is represented by a logarithmic curve on a graph. O of n is linear time, and as you might expect, this is represented by a line. O of n squared is represented by a parabola, and this is where we start to get into exponential time. Now, for things over 4, O of 2 to the n is where we start getting into more difficult problems, and after that we start getting into non-deterministic polynomial time. If you have seen my earlier video about the P versus NP problem, you probably recognize non-deterministic polynomial time is also referred to as NP. If you are the curious type, you're probably wondering how runtime complexity is determined. This is a good question, but I do not have time to go over it fully here. But if you have something like sequential blocks of code that will run the same amount of time regardless of the input, you essentially have a runtime complexity generic category of O of 1. You may have a specific runtime complexity category that equals the number of statements you've put in the sequential block. If you have a for loop and only one of them, you have something that can be represented as a graph as far as the runtime goes. Naturally, the more inputs you have for the for loop, the longer the loop will take, but it will increase in a linear manner. After the linear runtime complexities, we have the types of graphs that require curves. The first example of this are nested loops, most often nested for loops, although nested while loops are also possible. We can reduce these runtime complexities to n squared. If we want to work out a more exact runtime complexity, we could probably do it on paper or a whiteboard. Unfortunately, I'm doing this in a PowerPoint slide, and I did not plan far enough ahead to do it that way. After that, we also have the 2 to the n runtime complexity, and this is where we start to get into NP hard problems. All of this may be interesting or it may not be. I don't know. That's up for you to decide. But if you are interested in this sort of thing, you're probably wondering why we worry about it at all. The answer is that hobbyists usually do not need to worry about this. Video game designers often don't need to worry about it either, although they should keep it in mind for the algorithms that require more complex tasks, and especially ones that eat up GPU processing space. Programmers working for larger organizations, however, need to make sure to reduce the time the algorithms take because this can save companies money, and taking the least amount of time it takes for an algorithm to run makes the users happier. After all, if we had to wait 1 hour for our Amazon results for something we're looking for, we wouldn't use Amazon all that often, and we would probably go to our local department store and shop there instead. And we all know that we all don't love department stores and shopping in person anymore. If you followed along to this point, I would like to thank you for sticking with me. You're probably thinking, if you weren't into this in the first place and are still watching, that this all sounds rather nerdy. I'm going to assure you that it is. But if you're complaining that it sounds rather nerdy, why are you watching my channel? There are other YouTube channels that don't challenge you to think, or challenge you to think a lot better than this one does, and I'd recommend you to go watch whichever one falls into your specific needs. If you would like to find out more about big O notation and how it works, or don't feel I've covered it particularly well, I have put some links below, and I've misspelled Quantum Magazine's name. Some of them are videos, some of them are articles on a website, and of course, I've even included the Building Blocks for Theoretical Computer Science textbook, which is the one I used for my discrete math textbook, where it has an entire chapter on big O notation. Yes, I know it's a discrete math textbook, which can be a source of an overwhelming sense of revulsion for some people, but it is a useful resource in this case. If you have watched these videos long enough, you know the last slide always includes some math fun. I'm not sure if the math is fun or not, and I know the channel is only 2 weeks old at this point. I pulled the problem 3 to the 4th power divided by 3 squared from the internet. We want to find out what number is equivalent to it. We could work this out on a calculator, or we could use the old arithmetic method and get the valid answer, but I think there's an easier way to do this. We can determine what the easier way is by rewriting it. When we rewrite it, we get 3 to the 4th over 3 squared. And if we rewrite it that way and have taken enough math, we know that we can use the laws of exponents to do this. We're going to subtract the number in the denominator from the number in the numerator. If it's positive, we have a whole number. If it's negative, we have a fraction. So we're going to subtract 2 from 4, or 4 minus 2, and we're going to get 2. So since it's positive, we know the result is 3 squared, which is equal to 9. Perhaps I will cover a video on the laws of logarithms later. If you have any suggestions for a topic you would like me to cover, please let me know in the comments below. If you have any other math problems you would like to solve or argue about, please also add those to the comments section. Remember everyone, have a good day.